The closest star to Proxima Centauri, our solar system, has long served as a focal point for astronomers. This diminutive red dwarf, identified in 1915 by Robert Innes, a Scottish astronomer, is an essential part of the Alpha Centauri system, which also includes Alpha Centauri A and B. Despite its proximity, approximately 4.24 light-years away, it remains imperceptible to the unaided eye due to its comparatively low luminosity. Nonetheless, Proxima Centauri holds significant scientific importance, particularly as the host of the exoplanet Proxima B, located in the star's habitable zone. Red dwarfs like Proxima Centauri are cooler, smaller, and possess significantly longer lifespans than stars like our Sun. Their subdued brightness makes them challenging to observe. Yet, this characteristic places their habitable zones much closer to the star. In the case of Proxima Centauri, this translates to an orbital distance of merely 0.05 astronomical units, a fraction of the distance between the Sun and Earth. This closeness subjects Proxima B to intense stellar activity, including regular solar flares and higher radiation levels, creating an environment markedly different from Earth's. The discovery of Proxima B was a remarkable achievement in the study of exoplanets. Using the radial velocity technique, astronomers observed nudges in Proxima Centauri's position due to the gravitational pull of an orbiting planet. These oscillations enabled scientists to determine the planet's mass and orbital period. In 2016, the European Southern Observatory officially confirmed the existence of Proxima B, marking a significant milestone in the search for potentially habitable worlds beyond our solar system. While ground-based observations have provided valuable insights into Proxima B, they are constrained by significant limitations. Atmospheric distortion and light interference hinder terrestrial telescopes, preventing precise information about the planet's surface or atmosphere. As a result, much of the data we have, such as its mass, distance from the star, and orbital features, relies on indirect measurements. To gain a deeper understanding of Proxima B's environment and its potential to support life, advanced observational tools like the James Webb Space Telescope JWST are essential. Proxima Centauri's role as a gateway to comprehending exoplanet systems cannot be overstated. As the closest star system to Earth, it presents a unique opportunity to study the conditions necessary for life. Proxima B, in particular, offers an intriguing possibility: a rocky, Earth-sized planet with the potential to harbor water and possibly life. However, the challenges posed by its harsh environment render it a complex puzzle for scientists to solve. The James Webb Space Telescope is not merely another instrument in astronomy. It represents a revolutionary advancement designed to surpass the Hubble Space Telescope. While Hubble has provided important insights into the universe, its capabilities are limited to visible and ultraviolet light. JWST, on the other hand, is designed to observe the universe through infrared wavelengths, allowing it to peer through vast clouds of dust and observe phenomena Hubble cannot see. One of JWST's primary design features is its primary mirror, which spans an impressive 6.5 meters in diameter, more than twice the size of Hubble's mirror. This larger mirror enables JWST to collect significantly more light, allowing it to observe very distant and faint objects. Coated with a thin layer of gold to enhance its infrared reflectivity, the mirror's 18 hexagonal segments work in unison to create an extremely sensitive observational platform. Another revolutionary development is JWST's sunshield, which keeps the telescope's instruments at a steady temperature of around -233 degrees Celsius. This ultra-cold environment is critical for detecting faint infrared signals without interference from the telescope's own heat. Unlike Hubble, which orbits Earth, JWST operates from the second Lagrange point L2, a stable position approximately 1.5 million kilometers from our planet. This location minimizes interference from Earth's heat and light, allowing JWST to conduct continuous observations. The telescope can study everything from the earliest galaxies to the atmospheres of exoplanets like Proxima B. Its sensitivity to infrared light is especially significant because it enables scientists to focus on red-shifted phenomena objects, whose light has been stretched to longer wavelengths due to the universe's expansion. JWST's capabilities extend beyond mere observation. It is designed to address some of the most fundamental questions in science, including the origins of galaxies, the formation of stars, and the conditions that could sustain life on other worlds. Equipped with state-of-the-art instruments such as the near-infrared camera NIRCam, the mid-infrared instrument MIRI, and the near-infrared spectrograph NIRSpec, JWST is not just a telescope. It is a time machine, a laboratory, and a testament to human ingenuity. Proxima B has captivated researchers and the general public alike as a potential second Earth. Situated within its star's habitable zone, the planet possesses conditions that might support liquid water, a key element for life as we know it. With a mass approximately 1.17 times that of Earth, Proxima B is likely a rocky planet with a composition similar to our own. Its proximity to Earth, at a distance of 4 light-years, makes it an ideal target for studying the possibilities of life beyond our solar system. However, Proxima B is far from an ideal twin of Earth. One of its most striking features is that it is tidally locked, meaning one side of the planet is in perpetual sunlight while the other is in eternal darkness. This results in a unique climate with significant temperature differences between the two halves. The region where day meets night, known as the Terminator Line, may provide a temperate climate where liquid water could persist and biological processes could potentially occur. The environmental challenges on Proxima B are significant. Our Proxima Centauri is well known for intense and powerful stellar flares, ultraviolet, and X-ray eruptions of radiation. These energy outbursts have the ability to gradually diminish the planet's atmosphere, exposing the surface to hazardous space weather. To retain an atmosphere under such conditions, Proxima B probably requires a powerful magnetic field to protect and ward off this radiation. Without such protection, the surface of the planet would be extremely hostile to established types of life. Nonetheless, the chance of life persists. Where Proxima B stands within the habitable zone suggests that liquid water may or may not exist on the surface, but below-ground reservoirs, where conditions are more stable, could exist. Scientists, therefore, draw comparisons with extremophiles on Earth organisms that thrive in extreme environments like deep-sea regions or hydrothermal vents with high radiation. If Proxima B is inhabited, it may rely on similar adaptive strategies for dealing with radiation, alternative habitats, or underground biochemical routes. The exploration of Proxima B is more than just a scientific discovery. It represents a journey through philosophy and existence, resolving one of humanity's most fundamental questions: are we the only ones in the cosmos? An Earth-sized planet that resides in the habitable region of our closest stellar neighbor presents an attractive opportunity to explore this question. Technological capabilities are steadily rising as a result of advancements in observation, analysis, and interpreting signals from distant worlds. Although Proxima B entices, it is fundamentally shaped by its environment and the characteristics of its star. The red dwarf Proxima Centauri is not only smaller and cooler than the Sun, but also significantly more active. This means its habitable zone is extremely close, less than 5% of Earth's distance from the Sun, resulting in the planet's constant and tight orbit, exposing it to flare activity. These stellar flares, far more frequent and forceful than those from our Sun, generate streams of high-energy particles that bombard Proxima B. Without a robust magnetic field, the planet's atmosphere could be eroded over time, leaving it exposed to radiation. Even when an atmosphere remains, the intense ultraviolet light could hinder the development of intricate organic molecules, making it difficult for life to emerge or endure. Earth offers examples of organisms that have developed adaptations to radiation-heavy environments. Deinococcus radiodurans, also known as the toughest bacterium on Earth, is able to repair severe DNA damage. If life exists on Proxima B, it might have evolved similar or even more advanced mechanisms. Additionally, tidal locking may provide a natural barrier. The perpetually dark side of the planet could serve as a refuge from radiation, as could subsurface environments like caves or underground oceans, which may provide additional security. All of this makes Proxima B an incredibly valuable testing ground for astrobiology. Studying its environment might challenge our understanding of habitability beyond Earth-like conditions. It provides a practical framework for testing hypotheses regarding the resilience of life in extreme circumstances. Its proximity to Earth means we can continue to monitor it using existing instruments like the James Webb Space Telescope JWST and next-generation observatories in development. The inquiry into whether Proxima B is habitable remains open, but its discovery has already enriched our grasp of the universe. It is one of many exoplanets in a growing catalog of potentially livable worlds. The James Webb Space Telescope is expected to improve this understanding by detecting and analyzing the atmospheres of distant planets with unmatched sensitivity. JWST's spectrometers can identify specific chemical signatures in planetary atmospheres, such as water vapor, carbon dioxide, and methane, which could point to biological processes. Monitoring these indicators will be crucial in determining whether a planet could support life and whether life might already exist. While Proxima B has garnered much of the spotlight due to its proximity and conditions, it is not alone. Other exoplanets orbiting Sun-like stars, including some found by missions like the Transiting Exoplanet Survey Satellite TESS, are excellent candidates for further investigation. The more planets we find in their stars' habitable zones, the clearer it becomes that the universe might be full of opportunities for life. These discoveries also underscore a broader challenge, understanding the interplay of factors that truly define a planet's habitability, the makeup of the atmosphere, stellar activity, geological processes, and more. As space exploration technology advances, so does our ability to directly examine planetary climates and surfaces. Upcoming missions may follow in the footsteps of successful Mars rover programs or target the icy moons of Jupiter and Saturn. These projects will help us comprehend how environments might sustain life far different from Earth's. They will also influence our exploration of Earth-like exoplanets such as Proxima B. In the end, the pursuit of life beyond Earth carries profound consequences for our understanding of ourselves. Proxima B might not be a second Earth, but it shows that habitable environments are not restricted to our planet of origin. The need for ongoing research, exploration, and technological advancement is obvious. As we broaden our reach into space, the coming decades promise breakthroughs that could forever change our perspective on life and the universe. Whether it is detecting microbial life on Proxima B or locating a more Earth-like planet in a distant star system, each step brings us closer to answering one of the most essential questions of existence. The study of distant stars and their worlds, once the domain of science fiction, is becoming one of humanity's most thrilling scientific frontiers.